It's stuff I can verbalize.
Okay.
Okay. So it says find the exact value of the trigonometric function at the given real number.
Okay.
And so the first question is sine of 2 pi over 3.
All right. Have you learned, you've obviously learned how to convert degrees to radians and back and forth, right?
Right.
So with most trig students, the tendency is to convert everything to degrees just because you're more familiar with degrees.
Right.
And that's fine. There's no problem with doing that. After a while, just like with any foreign language, you get so you can almost think in terms of radians.
Right.
Now, when you get to calculus, calculus only works on trig functions if they're in radians. So once you get to calculus, everything is in radians, and you don't deal so much with degrees anymore.
Well, I can kind of think in terms of both. Like
Good.
looking at that, it's pretty obvious to me that it's 120 degrees.
Okay. Let me tell you one thing that helps a lot is this. Notice that that times that is 180. That times that is 180, and that times that is 180.
Right.
So,
Well, pi is 80.
yeah, whenever it's just pi in the numerator, it's real easy to convert. But
Right.
one advantage of this is that 2 pi over 3 has to be two of those. So it's got to be 120. So
Right.
you're
Also,
dealing
2
with
pi is
numerators other than
obviously
1. Yeah, you can use this system to do the conversion rapidly.
right. And 2 pi, if you know that 2 pi is 360, you just divide that by 3.
That's true. You can also do it that way. There's all kinds of ways to do it. And you can obviously use the conversion factor 180 over pi.
Right.
However, the crux to this is not really whether it's in degrees or whether it is in radians. It's being able to figure out the reference angle. You've learned about reference angles?
Yes.
The reference angle in the second quadrant is 180 minus theta, or if you're dealing in radians, it's pi minus theta. In the third quadrant, it's theta minus 180, or theta minus pi. And in the fourth quadrant, it's 360 minus theta, or 2 pi minus theta. And the last thing that I use is all students take calculus. Have you learned that?
Mm-hmm.
Okay. So whenever I get an angle that is not a first quadrant angle, then my goal is to figure out what the equivalent first quadrant angle would be using these formulas. Most of the first quadrant angles you probably have memorized. You probably know what the sine of 30 degrees is. If you don't have them memorized, then you want to memorize these two special triangles, the 30-60, and this is more important for trig than it is for geometry. Just because trig, they expect you to be able to do the common angles without a calculator.
Right.
So if I said, what's the sine of 45 degrees, as long as you knew this triangle here, you could figure out it has to be 1 over root 2, which
Right.
might have to rationalize, but still it's the same number. And So if I'm dealing with the sine of 2 pi over 3, which quadrant's that in?
2 pi over 3 is in the second, the second quadrant.
So I'm going to use pi minus theta to figure out the reference angle. And
Okay.
the reference angle is the equivalent first quadrant angle. Okay? In other words, 2 pi over 3 is, as you said, 120 degrees. So there's our 2 pi over 3, which leaves a reference angle of pi over 3. So the first thing I do is figure out what the reference angle is by using this.
60 degrees.
Correct. And now what's the sine of 60 degrees?
Sine of 60, so sine of 60 degrees is square root of 3 over 2.
Correct. Here's the way I like to do it. In parentheses, I put what the reference angle is. And whatever the sine of pi over 3 is, that's going to be the absolute value of the answer. Now is all I have to do. The third and final step is to attach a plus or minus sign to it. So what is the plus or minus sign in the second quadrant for the sine function?
The plus or minus sign is positive.
Correct. And that's the way I do all of these problems. They may have, different school systems work differently, but they may have suggested that you memorize what they call the unit circle, which has 16 spots on it, and they want you to memorize every one of them. Well, to me, that's insanity. It is. Because we don't, as humans, we don't memorize 16 things well. But what we do memorize well is stuff that's got 3 or 4 items in it. So if I can memorize all of the first quadrant trig functions, well, I can take any trig function that's in second, third, fourth, or higher quadrants and base everything on the first quadrant. For example,
and that's because of the reference angles, correct?
Yeah, what is the cosine of 225?
225, the reference angle for 225 would be,
so first place it's quadrant. Which quadrant is it in?
third.
So figure out which one of these you want to use. They're both the same. One is for degrees, the other is for radians.
Theta minus 180, which is 45.
Exactly. So in parentheses, I'm going to write 45. And what's the cosine of 45, looking at these two triangles?
1 over square root of 2.
Now, that's the right answer, but it needs to be rationalized. Do you remember how to rationalize that?
The square root can't be in the bottom.
Correct. So I have to multiply top and bottom by root 2.
So you get root 2 over 2.
And that is considered typically the answer to what's the sine or cosine of 45 degrees. Now, we're in the third quadrant, so what plus or minus sign do I need to put on that? In other words, we're not quite done. We came up with the reference angle was 45 degrees, and the cosine of 45 is root 2 over 2, but in the third quadrant, what's the sign?
Minus.
Correct. In other words, in the second quadrant, it's only sine and cosecant that are positive. In the third quadrant, it's tangent and cotangent. And in the fourth quadrant, it's cosine and secant. because the reciprocal has to be the same sign as its reciprocal.
And the ones you have to memorize are, like the ones that should be memorized are 30, 45, 60, and 90, correct? And 0.
Well, and all of the quadrangles. In other words, not just 90, but 180 and 260.
Right, although, but they're in reference, like 180
well, you cannot get the 90-degree angle from these triangles. I mean, you can, but it takes some real out-of-the-box thinking. So you need a different way to memorize the quadrangles. Do you know what, like, the sine of 90 is?
The sine of 90 is 1.
Okay, so there's two ways to memorize the quadrangles. One way, which is the one I favor, is to memorize that curve right there. Knowing that that's the sine curve, it goes up to 1, it goes down to -1, and there are 4 quarter points. In other words, when I say memorize it, you need to memorize each of these points.
Oh, I know them, yeah.
And now, it's really easy to answer the quadrangles. What's the sine of pi over 2?
The sine of pi over 2 is...
Read it off my graph.
It's 1.
Correct. What's the sine of 3 pi over 2?
-1.
Correct. And I've only drawn one period of this. It's important to understand that it does go on forever in both.
Yeah, the next thing we're going to do, the next thing after we get through this part of the questions, I'm good with sine and cosine. I need a little help with tangent, cosecant, and secant.
Well, let's talk about the graphs. Now you know what the cosine looks like. Let me draw the cosine in blue. Cosine drops down to 0 at pi over 2, goes down to its lowest value at pi, comes back up through 3 pi over 2, and finishes where it started.
Right.
Tangent.
I know it has a period of pi.
Correct. And it also has something that cosine and sine don't have, which is vertical asymptotes. And it's going to have a vertical asymptote every pi.
Which I don't understand what an asymptote is.
Okay. This is at minus pi over 2, and that's at pi over 2. So the period is from minus pi over 2 to pi over 2, which is a period of pi.
Right.
An asymptote means that as we get close to either minus pi over 2, tangent goes to negative infinity.
It will never reach pi over 2.
It's undefined at pi over 2.
Okay.
And that's because tangent is sine over cosine. And cosine of pi over 2 is 0. So you would be dividing by 0. And that's what makes it undefined.
Undefined.
You can never divide by 0. Okay? And so tangent of minus pi over 2 is undefined, or negative infinity according to our graph. And tangent of pi over 2 is undefined, or positive infinity. And it just repeats every asymptote. In other words, there's an asymptote every pi, and the tangent curve is always like that. And the key point on the tangent curve is that point right there. The tangent of 0 is 0.
Right.
And the difference between the tangent and the cotangent. The tangent, notice, goes from minus pi over 2 to pi over 2. Well, the cotangent has its own vertical asymptotes because it's equal to cosine over sine, so whenever sine is 0, it's going to be undefined. And
Sine is 0 at 0.
Looks very similar to tangent, only it's an always decreasing function, like that. And the reason that's important, and it goes between 0 and pi. In other words, its vertical asymptotes, it also has a period of pi, but its vertical asymptotes are every multiple of pi, not pi over 2. And notice the difference between tangent and cotangent. Cotangent's always decreasing.
Right.
Tangent's always
a negative cotangent? A negative cotangent, like a
that's when it gets confusing, is when they give you either a negative tangent, because the negative in front of the tangent means you're going to reflect it over the x-axis.
But doesn't that they're kind of interchangeable in some cases?
Only if you adjust it horizontally. Notice,
right,
if I told you graph y equal negative tangent, let me go back to red. If I said y equals negative tangent of x, well, I'm going to flip this, which would make it look like this. But notice that it's still going from minus pi over 2 to pi over 2. It's not exactly the same as the cotangent curve. The cotangent curve goes from 0 to pi.
So tangent crosses 0.
Yes, at 0.
So wait, if you had minus tangent plus pi over 2, that's a cotangent graph.
Yeah.
Okay.
Absolutely. They are shifted by pi over 2. In other words, first of all, if I show you just a curve, in other words, if I put a curve out here like that, you can't really tell without that curve being labeled, the x-axis that is, you cannot tell whether that's a cotangent curve or a negative tangent curve. But if I put the asymptotes in there, and I say that's pi, and that's 2 pi, now what kind of curve is that?
That is a cotangent graph.
Correct.
Negative cotangent graph.
No, cotangent. Remember, cotangent's always decreasing. So it's either a cotangent curve or a negative tangent curve.
So it's a cotangent curve, or it's negative cotangent plus 3 pi over 2.
Well, when you say plus, I hope you're putting that in parentheses. In other words, yes and no. It's not negative tangent plus pi over 2 like that. It's negative tan of x minus pi over 2 inside the parentheses like that.
Right.
In other words, this is a horizontal phase shift.
Right, yeah.
Whereas if it's outside like that, it's a vertical shift.
Vertical phase.
So be careful about that. And they're drastically different with trig, because the vertical shifts are going to be in terms of numbers like 1, 2, and 3, whereas the phase shifts are going to be in terms of radians, like pi, pi over 2, pi over 4, things like that. And the horizontal phase shifts always go inside the parentheses.
Right. And I knew that too. But I spoke wrong.
Secant and cosecant.
Yeah, that's where I have trouble. And I know that secant is related to the cosine graph, and same with like
all you have to remember is which one is the reciprocal.
Secant is
curve,
for
what curve did I just draw?
sine.
So that's y equals sine x. What's the reciprocal of sine?
Cosecant.
Which means when the sine is equal to 1, cosecant has to equal 1. So they both have to share that point right there. Which means the cosecant curve sits on top and bottoms of the sine curve, like that. And it also has vertical asymptotes because, again, since it's the reciprocal of the sine, whenever sine is equal to 0, when we take its reciprocal, we're going to be dividing by 0. And you will notice that these asymptotes occur where sine is equal to 0. There, and there.
Okay. That makes sense.
And it has the same period as sine and cosine, which is 2 pi. In other words, it goes from 0 to 2 pi to draw one full period of the cosecant. Because a full period of the cosecant, you need the part that goes up and you also need the part that goes down.
Right. And on a secant graph, it would be related to cosine.
Exactly. On a secant graph, you can look at this all kinds of different ways. I tend to think of, I got the 3 primary trig functions memorized down pat. So if I can draw those, I know I can draw the secant and cosecant because I know that they have to sit on the tops and the bottoms of my sine and cosine. So as long as I can remember which reciprocal goes with sine, cosecant, this got to be the cosecant curve. Because when sine is equal to 1, cosecant has to equal 1. The reciprocal of 1 is 1. Okay? Now, if I want to do secant, you don't have to do it this way. It's just I find it a little easier to start out with the cosine curve. And we'll put a full extra period on there. And that's y equal cosine x. So whenever cosine is equal to 0, I'm going to have a vertical asymptote. So I got to have a vertical asymptote right going through there. Got to have a vertical asymptote going through there. And the secant curve is going to sit on the tops and the bottoms of my cosine curve. I have another asymptote there. Wherever cosine is equal to 0, well, secant has to be undefined.
And so if you were to shift the graph, you could get...
Yes.
Just like you can get sine and cosine to shift, you can get cosine...
Sine and cosine are phase shifted by 90 degrees. So I can take the cosine curve and notice that if I take this cosine curve and move everything over 90 degrees, what's it look like? It looks like this. That's the sine curve.
Yeah, exactly.
So the cosine of x minus pi over 2 is the same as the sine of x. And there's always multiple ways. In other words, given any curve that they're going to give you, you can come up with multiple trig functions that represent that curve if you include phase shifts.
There's an infinite amount.
There are, but there's kind of a general rule in math that you use whichever one has the smallest phase shift.
Okay.
In other words, I'm never going to call this curve cosine of x minus pi over 2. I'm always going to call it sine of x because it has no phase shift if I call it sine of x, this curve right here.
Right, it's simpler.
Yeah, it's correct to say that that's also the cosine of x minus pi over 2. but I wouldn't ever use that because it involves a bigger phase shift. And in fact,
okay.
you get problems where there's some sort of a phase shift and you have to decide whether to use sine or cosine. You should pick the one that has the smallest phase shift.
Right.
Like a Ferris.
It's just right now in class because we have to list like one or two of each for each.
So I'm assuming that you have had this, the sinusoid function. May have been given to you with variables other than A, B, C, and D, but
yeah, we had they I don't remember what we had. I think we have A, sine, K.
Okay. Regardless of what letters you use, the three key letters, there's your vertical stretch factor.
Right.
There's your horizontal stretch factor.
That's the period, right?
Yeah. Well, no, I call it a horizontal stretch factor. In other words,
that's not the period.
If I had this curve here, and that's sine of x, sine of 2x is going to look like that.
Right.
I'm going to compress it horizontally.
It's not the sine. It's not the period, but you divide it. You divide that number.
Yes. That's the thing to remember.
Divide the period by that number to get it.
The period is equal to 2 pi over b, which makes b equal to 2 pi over the period. And a lot of times they'll give you the period and you have to figure out b, or they'll give you b and you have to figure out the period.
Right, exactly.
Okay. And now, there is a tricky part to this b, and it's the only one that really is tricky. And that depends on whether the b is inside the parentheses or out. You might get an equation that has the b inside like that. In other words, I can certainly give you an equation like this. The b is inside, right?
You have to divide that whole inside by 3 to get it out, right?
Factor out the 3, exactly. In other words, I would want to write this the following way. I'm going to factor out the 3, and what that leaves inside is actually, now it's this. And
right, exactly.
Once I get it into this format, now this is the amplitude, this is the stretch or compress factor, this is the phase shift, and this is the vertical shift. Notice when I wrote it, the middle line, pi over 4 is not the phase shift. You only get that to be the phase, in other words, C is not the phase shift unless the B is outside of the parentheses. So if they change the middle one just slightly, you wouldn't have to change it much, put the parentheses there, now the phase shift is pi over 4 because my multiplier of x is outside the parentheses. I no longer have to factor it out. So there's multiple formats that they teach. In Colorado, believe it or not, they actually have 3 formats. They have the B outside, they have the B inside, and then some of them use plus C and tell you that the phase shift is minus C over B. So you have to be a little careful and know exactly what format you're dealing with when they give you the function. So let's make one up here. Have you had anything this complicated where they give you an A, a B, a C, and a D?
Yeah.
Okay. So when I get this, and the job is to graph it.
Right.
A is what? Let's just go through them all.
A is 2.
B is
4.
Which means the period is what?
2 pi. Oh, well, yeah.
It's 2 pi over B.
Which is 2 pi over 4, which...
So the period is pi over 2. So when you get a B, you always have to figure out what the period is. It's not like amplitude, where that's a piece of cake. When you're dealing with a B, you have to figure out what the period is in order to graph it. C is what?
Take that, 5. I mean, no, it's negative pi over 4.
Actually, it depends on how you think about it. The standard is x minus c.
Right. When
so
it's positive, it's actually minus.
The phase shift is positive pi over 4.
Right.
Which means it's to the right pi over 4. Positive, you go to the right. Negative, you go to the left. So in this function right here, the phase shift is a positive pi over 4, meaning I have to move everything to the right. And then finally, D is 5, and that's just vertically up by 5 units. You can take your horizontal line of symmetry, and that's the first step. In other words, if I wanted to plot this, my very first step is to move everything up 5 units.
Right.
And graph about that dotted line. Now, my amplitude is 2, so I know that I'm going to go up 2 units to 7 and down 2 units to 3. My graph is going to, if I didn't have any phase shift, I know my period is pi over 2, which means I have to finish the graph by pi over 2. So if I ignore the phase shift, I would graph it like this.
Right.
And there's 2 ways you can do a phase shift. And that's the hard way and the easy way. I always used to do it the hard way, which is to graph it without the phase shift, and then to regraph it using the phase shift. Well, the phase shift is pi over 4, so I'm going to go to this point, pi over 4, and I'm going to start my graph there instead of back at 0. And I still have to go a total of pi over 2, period. Okay?
Right.
Now, the best way to do phase shift is to start at the phase shift. I don't have to worry about drawing the original curve. There's no need to draw that curve right there. The way to handle phase shift is you start at the phase shift right there. You figure out what the period is. Well, the period is pi over 2, so that point right there has to be pi over 4 plus pi over 2. What is that? That's 3 pi over 4. And then I quarter that up. In other words, if that's pi over 4 and that's 3 pi over 4, well, that's got to be 2 pi over 4.
Wait, why is pi over 4 plus pi over 2 3 pi over 4?
Pi over 4 plus pi over 2, which is 2 pi over 4.
Oh, okay.
You get 3 pi over 4.
Right.
But the key is really quartering it up. In other words, one of the really important processes here is finding their start and your end. I know I'm starting at pi over 4. I know I'm ending at 3 pi over 4. So I have to quarter that space up to figure out exactly how to graph it. I have to find the midpoint. That's where it's going to go through. And then that point right there must be 3 pi over 8. And this point right here has to be 5 pi over 8. And so I have my 4 quarter points. I know where it starts, pi over 4, I know it reaches its maximum at 3 pi over 8. I know it comes back through the line of symmetry at pi over 2, goes down to its minimum point at 5 pi over 8, and finally comes back to its starting point at 3 pi over 4. And that's exactly how I would graph whatever function they give me.
Okay.
And like I said, it might be a little more comfortable for you to do it the way I used to do it, which is to graph the non-phase shifted and then just move it right or left by the phase shift and draw the same shape. A phase shift does not affect the shape. It's like any horizontal shift of any polynomial function. It's not a stretch factor. It's a horizontal shift. It's like the vertical shift. If I look at this function, this sinusoidal function here, that changes the shape, that changes the shape. But the pi over 4 does not, nor does the plus 5. They merely move the curve left, right, or up and down.
Okay.
Okay?
Yeah, they don't change the shape.
Now, they're going to give you problems of both kinds, and you're going to have to be able to go either way. In other words, they might give you the sinusoid function and say graph it, or they might give you a picture of a graph and they say come up with the sinusoid function. Well, they're exactly reverse processes of one another. In other words, if I would have given you this blue graph, the very first thing you would have noticed is the line of symmetry is up 5, so you'd know what D is. The next thing you notice is that it goes from 3 to 7. Well, that makes A 2. The next thing you notice is that its period is pi over 2, which makes B 4. In other words, if you know the period is pi over 2, the period is equal to 2 pi over B, you can calculate that B had to have been 4. And finally, you can see that it's been phase shifted by pi over 4 to the right from a sine curve. And that's where I get that. Now, if it was a cosine curve phase shifted by pi over 4, well, just because this thing is called a sinusoid function doesn't mean you have to have sine here. You can just as easily use cosine. And the one that you use is the one that has the smallest phase shift.
Okay.
In other words, you're going to get problems like the Ferris wheel problem. I don't know if you've had these or not. And notice that the Ferris wheel can be modeled with a sinusoid function. Well, what if you were to get on the Ferris wheel right there? Well, the Ferris wheel, you're getting on at the low point and you're going to the high point. What function does that? Negative sine. Negative cosine. Negative cosine looks like this. Starts at the lowest point, immediately goes straight up to its highest point. The same thing you're doing on that Ferris wheel. Okay? So if I want to model the Ferris wheel, getting on at the bottom, I'm going to use a negative cosine curve to do so. Let's say, though, you don't get on at the bottom. Let's say that they've built a ramp and you get on right there. There's stairs here. You climb up to the top of the stairs and you get on the Ferris wheel right here. Well, now notice that you're starting at the midpoint and you're going up. What models that perfectly? Sine. Sine, if you draw a sine curve, you start at the middle you go up to the maximum, you come back to the middle, you go down to the low, and you come back to the start. Well, if I get on the Ferris wheel right there, I'm going up to the high point, I'm coming back to the middle, I'm going down to the low, I come back to my start. The perfect model of that Ferris wheel is using sine. And if I get on somewhere here, right below the middle, well, that's a sine curve that's been phase shifted to the right a little bit. In other words, let me phase shift my sine curve a little bit to the right, and now where do you get on? You get on right below the middle. And I'd be better off using a sine curve than a cosine curve phase shifted by a larger amount. And that's what determines which one you use.
Okay.
These are probably the toughest part of trig, is these kind of problems. Any kind of problem where there's periodicity, whether it's a Ferris wheel, whether it's somebody that's breathing, because think about breathing. At the top of your breath, your lungs are holding 4 gallons of air. You breathe out. At the bottom of your breath, the lungs are only holding 2 gallons. And then you breathe in again. So now you're back to 4 gallons of air. So that process can be modeled perfectly by a sinusoid function. Same thing with the tides, high tide, low tide. Same thing with the temperature based on the time of the year in a given location. It's generally the same temperature on January 15th in Alaska, whether it's January 15th, 2016 or January 15th, 2015. But the fact is that it's a periodic process. So anything that has a periodicity to it, you use the sinusoid function to model it, which is extremely valuable because there are literally thousands of things that have periodicity to it. If you have a swing that goes from left to right, and you're sitting down there on that swing, you're going to go this way, and then you're going to go back that way, and you're going to go back that way. That's periodicity. That action can be modeled by a sinusoid function. Now, probably at this point, since I'm not quite sure, it sounds like you're right in the middle of studying sinusoid functions, if they haven't given you word problems yet.
But we have learned sine, cosine, tan, cotan, secant, and cosecant.
Right. The sinusoid function is really no different than any, if I gave you y equal x squared. And now I tell you, well, y equal 2x squared, that's a vertical stretch factor, right?
Right.
The same way a is in the sinusoid function. And now I tell you y equals, let's do x minus 3 quantity squared. That's a horizontal shift, right?
Right.
Same as a phase shift. In other words, this thing is basically the same as c.
Yeah.
Or if I give you y equals x squared plus 10, that's a vertical shift. Same as d. So I'm not quite sure why, when they teach the sinusoid function, why they treat it so separately from standard translations. And if I stick a negative sign in that, it means the same thing. It's a reflection over the x-axis. So there's no difference. When I write it like this, it's the same as a polynomial function that's being vertically stretched or shrunk, that's being horizontally stretched or shrunk, that's being horizontally shifted and that's being vertically shifted. If I want to reflect over the x-axis, I'll put a negative sign there. If I want to reflect over the y-axis, I'll put a negative sign there. So you can think of sinusoid functions really being the identical. There's nothing different than your standard polynomial translations. There's 6 things you can do and only 6. You know, you can do 2 things vertically, you can stretch it or shift it. You can do 2 things horizontally, you can stretch it or shift it. And you can reflect over the x-axis or reflect over the y-axis. That's 6 things. The most important thing to remember here is what b is. b is 2 pi over the period, because you always have to make that translation, going one way or the other. In other words, if they give you a graph where you can measure the period, then you can figure out b using that one. If they give you b and they want you to graph it, well, you can figure out the period using that. So do you have a specific problem that we can do?
Let me
At this
look.
point, I'm just kind of generalizing the sinusoid function and how to treat it.
Right. Quick question back to what we were talking about a few minutes ago. For the different quadrants, quadrant 1 doesn't have a formula because it's already from 90 degrees.
Everything's positive in quadrant 1.
Right.
You're right. Everything is less than 90 degrees. Yeah.
Right. So then quadrant 2 is 180 minus theta or pi minus theta.
Right. Here's the way to memorize that. 2 is the same as 4, only 4 is 360 minus theta. And then quadrant 3 is the reverse of 2. That's the way I memorize it.
Okay.
Once you know this one, then you know 3 and 4. All you have to do is memorize what quadrant 2 is.
And sine of 45 is square root of 2 over 2, correct?
Yeah, and I can't emphasize this enough that the best thing you can do is to be able to create those 2 triangles from memory.
Right.
If you can create both of these from memory, then that's all you need to figure out the first quadrant angles. It doesn't matter. In other words, what is the secant of 30 degrees?
2 over square root of 3.
Correct.
Which
still has to be rationalized, but it's the same number after it gets rationalized as it is before. It's just not presentable as a final answer until you rationalize it. But you don't always have to rationalize it. Only at the end. Don't waste your time rationalizing these things until you get to a final answer, because sometimes it'll reverse itself and you won't have to rationalize.
Right. And then cotangent is cosine over sine.
Not really, because that would be hard to figure out. You'd have to do a lot of math there. Cotangent is the reciprocal of tangent. That's the way to memorize cotangent. It's the reciprocal of tangent.
So it's opposite over adjacent.
Right. What's the tangent of 30 degrees?
Tangent of 30 degrees is 1 over square root of 3.
So what's the cotangent of 30 degrees?
Square root of 3 over 1.
Exactly. So don't mess with the fact that tangent's sine over cosine and cotangent's cosine over sine. If I did it that way, I'd have to figure out the sine of 30 degrees and the cosine of 30 degrees and then divide those 2 fractions. In other words, I do know that tangent is equal, that's an identity, sine over cosine. So if I said, what's the tangent of 30 degrees? Well, sine of 30 degrees is 1/2. cosine of 30 degrees is square root of 3 over 2. Well, now when I simplify that, I get 1 over square root of 3.
Okay. What if the number is negative that's in there? Such as secant of negative pi.
Okay. Glad you asked that. There's two ways to do that. Again, one is the hard way, the other is the easy way. Here's the easy way. Both of these functions are odd. That's why the sine of negative x is equal to negative sine of x. That's what odd functions do. Cosine is even, meaning the cosine of negative x is actually equal to the cosine of x. So if I said, what's the cosine of minus 60 degrees? Well, you would say that's the same as the cosine of 60 degrees, which is 1/2.
Okay.
The other way to do it, which again, I used to do it the hard way, is to take that negative 60 and turn it into a positive angle. Well, that's the same as the cosine of 300, right?
Right.
But then, in order to do the cosine of 300, I'm in the fourth quadrant, so I have to do 360 minus 300. So the equivalent first quadrant angle would be 60. And I know that that's 1/2, and now I see it's in the fourth quadrant, so I know that its plus or minus sign has to be plus.
Well, what about for the other ones?
They share this property. In other words, cosecant has to be odd also. Cotangent has to be odd. And secant has to be even. In other words, you can't have cosine being even and secant being odd because they're reciprocals of one another. It's just like if the cosine is positive in the fourth quadrant, then secant is also positive in the fourth quadrant. Well, if cosine is even, secant is even also, meaning that the secant of negative x is equal to the secant of x. So let's take an example. Let's say the sine of minus 30 degrees. Let's do that one. What's the easy way to do it?
Negative sine of 30 degrees.
Yeah, and you know what the sine of 30 is. That's a first quadrant angle, so you know that's 1/2. So the answer is minus 1/2.
That's it?
I don't have to go through the rigmarole of saying, well, that's the same as the sine of 330 degrees, and then that gives me a reference angle of 30, but fourth quadrant I would be negative. In other words, you have to go through a couple of additional steps if you do it the hard way.
Right.
If you remember this odd-even stuff, it'll make all of your negative angles much easier to do.
Now, last question. What if, let's say it's not in the first or second quadrant, so it's sine of negative 270.
No, that's not an even one. Let's make it even. 135. Okay?
Okay.
Now, I can figure out that that is this angle. That's minus 135 degrees. So right. I know I'm in the third quadrant. Okay? Right. But let's just do it the easy way. It's the same as the sine of 135. Now, you still have to work through figuring out the sine of 135, but that's a second quadrant angle, right?
Right.
So it's the same as the sine of 45 which is square root of 2 over 2. This negative sign comes with it, so there's your answer.
Okay, so that's how it works.
Yeah,
But
in other words, no different. No different. It does not work any different. It's just you're dealing with a positive angle immediately.
So you're in the second quadrant.
Well, not really. In other words, that's a third quadrant right there.
Okay, so does it double
Once
negative?
I
Does it
use the
become
fact
positive?
that it's an odd function and I turn it into minus sine of 135, now temporarily I'm in the second quadrant for figuring out the answer.
But once it's back where it belongs in the third quadrant, does that become a double negative and then become positive?
No, sine's always negative in the third quadrant. So I better have a negative sign on that thing. Okay. It's just I got it differently than I normally would get it. I got it by turning this into minus sign of plus 135. And then I just dealt with let's figure out what the number on sine of 135 is. Well, sine is positive in the second quadrant, so the sine of 135 is root 2 over 2. But this negative sign comes with it. In other words, you're not ever in both quadrants. I'm not in the third and the second quadrant here. I'm in the third quadrant. It's just that along the way to figure out the answer, I go through the second quadrant. You see what I'm saying?
Right.
And that's the way to do it, is to use the odd-even property to turn it into a positive angle immediately. And then as long as you know how to do positive angles, just carry forth your negative sign, or not. In other words, if I'm dealing with the cosine of 135, a negative 135 degrees, well, I immediately turn that into the cosine of 135, and then whatever that gives me is my answer. But I am in the third quadrant. I am not in the second quadrant, even though I use this second quadrant to come up with the answer.
Okay.
Only because it's the easiest thing to do, as opposed to turning that into the positive 225. In other words, that's the same as the cosine of 225, and that is definitely a third quadrant angle.
Okay.
It's just more work to do it this way.
Right.
To take this temporary step here is less work.
Okay.
Once you immediately put it in a positive angle.
All right.
All right. Sounds like you're making pretty good progress through Trig. Or you must be about done with new material.
Yeah, we're actually going back to do a little bit of Algebra 2 with logarithms and whatnot, and then...
Yeah, usually that's what schools do, is they stop new material about this time of year and start reviewing stuff for your finals.
Right.
All right.
Okay, thank you.
Good luck, and I'll talk to you next time, Max.
All right, thank you.
Bye-bye.